Hi, welcome to 24th session on measure theory. This is the 7th session on Lebesgue integral. As indicated in the last session, the topic of today's session is the dominated convergence theorem. This is the most useful theorem. See, there are three major results which shows the strength of Lebesgue integral. They are essentially something to do with changing the integration with the limit of the sequence. Okay, roughly. The first one is monotone convergence theorem. There the assumptions were two. Every function fn is non-negative, and fn, the sequence fn is increasing. That is, for each x, fnx increases to f of x. Then we proved that integral of f is same as limit of integral fn. That's monotone convergence theorem. The next thing is Pathos lemma. There it said fn need not converge, but we still wanted fn to be non-negative. Then it showed what is the thing, integral of the lim-inf of fn. It showed is less than or equal to lim-inf of the integral fn. Okay. Now the third thing is dominated convergence theorem. So whenever you want to apply a sequence of functions and integration in Lebesgue theory, you have to look for one of the three. This is the trick. Okay. Obvious thing is, if I am given fn non-negative, I will use monotone convergence theorem. And I will come to the dominated. It says that each fn is measurable, but mod fn is less than or equal to g. But g I am assuming to be integrable. Right? And assume that fn converges to f, then f will be measurable. Then it says integral of fn converges to integral of f. Right? Here there is no assumption about the sign of fn, but then all fn's are bounded by a single measure integrable function g. That is the condition. Alright? If I have a sequence of functions, I have no idea whether it converges or not, but I want to say something, then naturally I have to use Pathos lemma. Keep this in mind, okay? As we go along, we will see a lot of applications. So the only way you can become comfortable with the Lebesgue integral theory is how to use convergence theorem, okay, judiciously. Okay, right. So let us get to work. So this is known as Lebesgue dominated convergence theorem. In short, I will call it DCT. MCT for monotone. Pathos is Pathos. Okay. What does it say? You start with, as usual, a measure space. Okay. Let fn a sequence of measurable functions. It could be RE, RC, measurable functions. Okay. Assume that two things. One, okay, fn converge to f point-wise. Okay. And two, there exists an integrable function, that is a g in L1 of x mu. Okay. So that mod fn is less than or equal to g for all n. This means mod fnx is less than or equal to g of x for all n in n and x in x. Okay. So in particular, my g must be non-negative. then the conclusion is integral fn d mu converges to integral f d mu. But actually we say something a lot more. We say that in fact integral of mod fn minus f d mu, this is a non-negative function, right? This converges to 0. Okay, this is stronger. Okay, you call this 1. Okay, this is 2. 2 implies 1, obviously, right? Because mod fn minus mod f integral, by linearity, I ought to show f is integrable. Okay, on the way. Yeah, that will be easy. Okay, this is fn minus f modulus, because this I can justify within modulus, this equal to this, I can justify only if integrable functions. So I need to show that f is integrable. Okay, but then by basic inequality, this is less than or equal to mod f1 minus f. Okay, that shows integral f1 converges to integral f. You understand this? Pause. Review. Proceed. As usual, it is important to understand the statement, try to internalize that rather than simply learn by heart. Okay, that's why I'm explaining that point wise. Okay, now let's go to the proof. So, first I will talk about some technicalities. Okay. And we are assuming I simply said fn's are measurable, but you can see I needed integrability, therefore let us assume these are integrable. Okay, I am making a correction to the statement of the Lebesgue dominated convergence theorem. So I want each of my fn to be integrable. It's not simply measurable. Whereas in the case of monotone convergence theorem and Patou's lemma, we needed only non-negative functions. We didn't bother about integrability. Non-negative measurable functions, no question of integrability. Here we are putting extra condition. Okay. Now look at fn. Okay. Now fn of x converges to fx. But each fn of x is less than or equal to g of x. Therefore, mod fx is also less than or equal to g of x. Right? Now, since fn converges to a pointwise, we know f is measurable. And mod f is less than or equal to g, where g is in L1. Therefore, by the observation we made, f is in L1. Right? Therefore, fn, f, g are all in L1. Right? The next thing is, we saw that, forget about this f, okay, general recall. If f is in L1, then we saw that f is finite almost everywhere. That is, the set of points x, that mod fx equal to plus or minus infinity, equal to plus infinity is of measure 0. Call this set yes, then mu of e is 0. Right? We had already proved it in the last lecture. So, let us look at this points, okay, set of points, let us call it at a dn, okay, set of points x, so that mod fn x is infinity, okay, and d to be set of points so that mod fx equal to infinity, and b equal to set of points so that mod gx equal to infinity. Okay, these are all sets of measure 0, therefore the union b union d union of dn, this is of measure 0. Quality. Right? Therefore, what I can do is I can modify for all x and e, I can define f1 of x equal to 0 equal to f of x equal to g of x. Okay? It may even be finite, but I don't have to worry about that. Okay? Right. Therefore, all these functions I can assume, therefore, without loss of generality, we may assume each fn fg is finite on X. Okay, this is a technical part. If you are not comfortable, so you can assume that's not a problem. And second thing, since I wrote plus or minus infinity, let us look at the first case. Okay, where f is a f is a function from x to r of e. Okay, that's the first case, real case. Okay, all right. F meaning all fn, f, g, etc. Right. Okay. So now what do you want to prove? I want to prove integral of fn converges to integral of f. Right? Okay. So notice that since mod fn is less than equal to g, that means minus g is less than equal to fn less than equal to g. Right? Therefore, fn plus g and fn minus, okay, you understand that? Add plus g, okay, this will be 0, therefore that will be greater than equal to 0. And similarly, g minus fn, that will be greater than equal to 0. Therefore, g, if you want g plus fn greater than equal to 0, g minus fn is greater than equal to 0. And these are all measurable, right? Now, where do they converge? G plus fn converges to g, and g minus fn also converges to, sorry, g plus f, and g minus fn converges to g minus f, pointwise, right? Okay. Therefore, what I want, the trick is, as I said, Fatou's lemma. So I want to do something with interchange the thing with the integral and the limit. Okay, there is no monotonicity. I am yet to prove dominated convergence theorem. Therefore, the only left out tool is Fatou's lemma. So I have to make use of that. For that, what do I need? I need non-negative measurable functions. Now, do I have them? You see that? Now I got non-negative measurable function, right? Therefore, I can apply Fatou's lemma, right? Therefore, by Fatou's lemma, integral of, okay, let me write, integral of lim inf of g plus fn, okay, that's less than equal to lim inf of integral of g plus fn. They're okay, right? But this is same as this is a lim inf of, therefore it is g plus lim inf of fn, right? But this is equal to what? This is a lim inf of. First notice that this is equal to lim inf of. Since these are all integrable and integral is additive, it's actually linear. Therefore, this is integral of g plus integral of fn. But that is equal to what? That is equal to integral of g plus lim inf of integral of fn. Do you understand that? Yeah? Okay. Now let's look at this. Now since fn converges to f, therefore lim in of fn is same as f. Therefore this I can write this as integral of g plus f. Do you follow that? Therefore what I have shown, integral of g plus f is less than or equal to integral of g plus lim in of integral of fn. Okay, this is what I have got, right? But this again by g and f are integrable. Integral is a linear map, therefore integral g plus integral f. That is less than or equal to integral g plus lim in of integral f1. Now notice that integral of g is finite, right? Therefore I can add minus integral g both sides. What will I get? I will get integral of f will be less than or equal to lim in of integral f1. Okay, call this as 2. This is clear? So pause, review, proceed. Now what is that I wanted to prove? I wanted to prove limit of integral fn. So the first thing is I have to show this exists. Okay, right? But this exists if and only if, since these are all integrable, finite, okay, if and only if lim sub of fn should be equal to lim inf of fn. Sorry, integral fn. Right? So if I get something like that, so I have to prove these two are equal. Lim sub of integral fn equal to lim inf of integral fn. I know lim inf of integral fn is less than or equal to lim sub. Therefore, if I prove lim sub of integral fn is less than or equal to this, and that's less than or equal to, which we already have seen, lim inf of integral fn, right? But that in turn is less than or equal to lim sub. Equality holds everywhere. Do you follow that? So that is what you want to prove. So how do I get lim sub? Again, recall, if an is a sequence in R extended, right, then lim inf of minus an is nothing other than minus of lim sub of an. Okay. Now do you realize why one has to learn lim sub lim inf? I'll quickly give a proof because I'm sure most of you may not have seen. It's a very easy result. If A is a non-empty subset of R, assume supremum infimum exists, then infimum of minus A, okay, what is minus A? Minus A is minus x in A, right, is minus of supremum of A. Okay, from that this follows, because this infimum of minus an is what you are looking at. Okay, that is minus supremum. After that is the limit of the sequence, therefore they are the same. Are you following? This fellow will be equal to this fellow without limit itself, because this will be infimum of minus an ak k greater than or equal to n. That is what is involved in lim in. Similarly in lim sub. Okay, so this is easy. Okay, right, now come back. Now what I want to do is, therefore I apply Pathus lemma now, the other one. You see that? We already applied G plus Fn. We also saw something more. G minus Fn's are also measurable. Yeah, and they are non-negative. Therefore let us apply Pathus lemma to G minus Fn, which are non-negative and measurable. Right? Therefore, what will I get? Again, let us look at quick thing. What is lim inf of G minus Fn? That is G minus lim inf of Fn. That is G minus F. Yeah. Therefore, what I have is integral of lim inf of G minus Fn is less than or equal to lim inf of integral of G minus Fn. This is what Pathus lemma. But this fellow is nothing other than integral of G minus F. But again, by linearity of the integral, this is integral G minus integral F. Is that clear? Now let's try to unwind. It's the same thing. Yeah. So this is a lim inf of, by using linearity, integral G, and again using integral of minus Fn is minus of integral Fn. Notice that linearity of the integral is used here. Okay, and that we proved only for integrable function. That's why we needed Fn to be integrable function. That is why in the statement I went ahead and changed Fn to be integrable. Right? Okay. Is it okay? But now this is nothing other than integral of G, okay, and then plus lim inf of minus integral F. Okay, but that by whatever I recall, this is nothing other than minus of lim sup of integral fn. Right? These are my ans. Lim inf of minus an is minus of lim sup of ans. Right? Therefore, what you have shown is integral g minus integral f is less than or equal to integral g minus lim sup of integral fn. This is 3. But as earlier, we add minus integral g to both sides, then I get minus f is less than or equal to, because these are all finite. Now you also see where you used g's are finite, integral g's are finite. That is g is in L1. Okay. This is less than or equal to minus lim sup of integral fn. Right? Therefore, that means lim sup of integral fn is less than or equal to integral f. This is my 4. Right? So, let us look at 2 and 4. Integral f is less than or equal to lim sup. Right? Therefore, 2 and 4 give integral f is less than or equal to lim inf of integral fn. That is always less than or equal to lim sup of integral fn. That is less than or equal to integral f. Therefore, equality holds. Therefore, limit integral fn exists. That's first conclusion. Second conclusion is that lim integral fn must be equal to integral f. Yeah? Pause. Review. Proceed. So, we proved the first part. Right? So, let us again quickly go through the statement of dominated convergence theorem. What is our assumption about the sequence? About two assumptions. Fn's are integrable and Fn converges to a pointwise. And the third important assumption is there exists a non-negative integrable function g such that mod Fn is less than or equal to g. Then what is the conclusion? Integral Fn converges to integral f. But we actually want to prove something stronger. Yeah? What is that? Let us go through that. So, we still have to prove integral mod Fn minus f, the limit is 0. Right? Okay. Now, how do I prove that? Notice that Fn minus f, these are all non-negative, and they are less than or equal to mod Fn plus mod f. That's less than or equal to 2g, but 2g is in L1. Because L1 is a vector space, g is in L1, 2 times g is in L1. Therefore, this sequence of non-negative functions is dominated by integral function. Therefore, by the first part, okay, integral of Fn minus f. And sorry, another thing is mod Fn minus f goes to 0 because Fn converges to 0. Right? Therefore, by the first part, integral of mod Fn minus f goes to integral of 0, which is 0. Okay? So, this completes the proof of dominated convergence theorem. Pause, review, proceed. Alright. Now, where did we use the fact we are dealing with real functions? That's because we needed to talk about lim in of Fn minus g, yeah, g minus Fn or g plus Fn, etc. Right? So that is where we needed. But the theorem is true, and there is a proof which is slick. Nowadays, almost all textbooks use that proof only. I also learned that proof from Rudin's real and complex analysis in early, somewhere in 70s. Okay, almost 50 years ago. Right. Okay, that proof is the most popular proof. That also works for extended real number system also, Okay, as I said in the beginning preamble of the proof, without loss of generality, we will assume my fn, f, g, they're all real valued. If it is complex value, there is nothing. Okay, they are finite everywhere. Either they take values only in R or they take values only in C. Okay, that assumption we can make. Okay, so now let us go through a slick proof. A second proof, somewhat slick. What you do is you still want to apply Mathu's lemma. But now f and f, g, they may be complex value. Okay, the only thing I know is mod f1 is less than or equal to g. And hence we conclude, since f1 converges to f, we also conclude mod f is less than or equal to g. Right? Okay, therefore, where do I get my thing? Look at the second part. This is the trick I want to use. Okay, in the real case, we used it, no? By understanding then, therefore, I look at this one, 2g minus mod f, f1 minus f. Right? These are all non-negative because f1 minus f is less than or equal to, as I said, f1 plus f, which is less than or equal to 2g. Therefore, this is non-negative. And these are all measurable also. Right? Therefore, I can apply Fathus lemma. Right? So, what does it say? So, what is the lim inf of 2g minus f1 minus f? Since f1 converges to this I is nothing other than 2g itself. Right? Because this will be lim inf of 2g, which is 2g minus, okay, lim plus lim inf of mod f1 minus f, okay, plus this is a lim inf of minus this, right? Are you following? Yeah, plus lim inf of this object, right? But I know f1 converges to f, therefore mod f1 minus f goes to 0. The limit itself is 0. Therefore lim inf of that object will also be 0. Therefore this is equal to 2g, right? Therefore by Fathus lemma, integral of 2g, which is equal to integral of lim inf of 2g minus fn minus f, the whole thing into d mu, that is less than or equal to lim in of integral 2g minus fn minus f. Right? Now, as I said earlier, again remember fn, f are in L1, therefore fn minus f is in L1, and if something is in L1, if its modulus in L1, therefore this is also in L1. And 2 times j, therefore this is sum of two L1 functions. Right? Therefore this I can write as lim inf of integral to g and then minus, and using linearity of the integral, minus integral fn minus f. Okay, but this is equal to integral 2g minus, now this is a lim inf of a sequence of numbers, right? This is modulus. Okay, not please, because we want real numbers to talk about lim inf. These are all modulus. Right? Therefore this lim inf is minus lim sup, right? Integral mod fn minus f. Right? Think of this as ans, the lim inf of minus ans equal to minus of lim sup of ans. Okay, right? Is that clear? Therefore, I have got 2g is less than or equal to this. Now, integral 2g is finite, right? Therefore, as usual, adding negative of minus integral minus 2g, that is, add to both sides, I am going to get 0 is less than or equal to minus lim sup of integral mod f and minus f. Right? Okay, what does that mean? That means lim sup of integral f and minus f modulus is less than or equal to 0. But remember, these are all non-negative numbers, therefore each integral is non-negative, therefore lim should be greater than or equal to 0. Right? And therefore, lim of integral f and minus f is less than or equal to lim sup of integral mod f and minus f, that's less than or equal to 0, that implies equality. Right? Therefore, the limit of integral mod f and minus f exists and equal to 0. So that's a proof. So notice that in this proof, we are proving, so we proved the second conclusion first. Second conclusion of the theorem first. Okay. Then integral f1 converges to integral f follows because I have to estimate integral of f1 minus integral of f. As I said earlier, this is modulus of integral f1 minus f because of linearity. But then that's less than or equal to basic inequality mod f1 minus f. That we know goes to 0. Therefore, this follows. And hence 1 follows. Yeah. So you saw the interesting thing. In the modified proof, okay, how did you modify the? We looked at the second part of the first proof, okay, and that gave us a second proof. In that we proved the second part first, first part next, right? So please go through both the proofs. It will make you more comfortable, and I'm sure most of you will prefer 2g minus mod f and minus f for two reasons. That is the common thing in textbooks nowadays. And second thing is that looks very small, right? Very easy. There I have to talk about limit and two things, right? I have to apply Fathus lemma twice there. If I remember right, g minus f1 and g plus f1, right? Or whatever it is. So twice I have to apply. Here I have to apply only once. So this is somewhat shorter and easier to remember. Yeah, it's up to you. Whatever you like, you take it. Okay. But I would like you to go through the proof at least once, both the proofs. Okay. Now I want to give some typical applications of dominated convergence theorem. Okay. Later we will give some more non-trivial applications, okay, of dominated convergence theorem. And finally, I will give some good examples, at least a couple of examples, 2 or 3 examples, in which, okay, how to use convergence theorem or Lebesgue integral. See, finally, the major point in learning measure theory is not construction of Lebesgue measure, outer measure, Lebesgue measurable set, non-measurable sets, etc. Finally, when I want to use, I am going to use integral. And as an analysis, I have to deal with the limits and integration. So how I can interchange is the major problem whenever I want to use integration. Okay. And therefore only there are 3 theorems on Lebesgue integral, namely monotone, Fatou, and dominated convergence theorem. So in the last session on this series, Lebesgue integral, I'll deal with some non-trivial examples just to illustrate. But remember, for each of the thing, MCT, Fatou's lemma, I had already given typical examples, okay, applications. So I am going to give typical applications for dominated convergence theorem now. Okay, let's go ahead. So application. Dominated convergence theorem. The first one is, let us look at function R n m2. Okay, R extended or C, etc. Right? Then I want to say I have, okay, let us look at f n to be f into indicator function of minus into plus n. Right? So this means I have minus n plus n. My f I take. Okay. Now my function will be only this one. After that is 0. Yeah, that's a function. Notice that fn converges f pointwise. How do I prove that? Start with in x. In R, choose n such that mod x is less than n. Sorry, yeah, mod x is less than n. Right? Therefore, this may be my minus n plus n. My x is somewhere here. Right? Therefore, f1 of x is nothing other than fx for all n greater than equal to n. Therefore, the sequence f1x, okay, after this particular n, which of course depends upon x, okay, for n greater than equal to nx, is a constant sequence. Eventually constant, therefore this converges pointwise. Right? Now, if I assume f is in L1, that is thing, then what do I have? My f1s are also bounded by f, mod f, and mod f is in L1 because f is in L1, right? Therefore, by dct, okay, integral fn converges to integral f. What does this mean? Notice that integral fn is nothing other than integral of f over minus into plus n converges to integral of f over minus into plus n. That's what it means. Local. So, pause, review, proceed. Okay. So, notice that you can generalize this. That is, suppose x b mu is a sigma finite measure space. What does it mean? X is union of en, ens are unmeasurable, and mu of en is finite for all n. Right? Then notice that with a loss of generality, I can assume ens are increasing. Right? Why? Define an to be e1 union ek. Then measure of an is finite because less than or equal to k equal to 1 to n of measure of ek, and that's finite. Therefore, each measure is finite, and of course an increases to x. Yeah. Therefore, we can assume en itself is finite. Right? So these ens are analogous to minus into plus n in R. Right? Therefore, I can define if f is in L1 of x be mu, I can define fn to be f into indicator function of ens. Then fn converges to f pointwise as earlier, and integral fn converges to integral f. That is, integral of f over en converges to integral of f over x. Okay? All review. So the only assumption we have to make on the measure space is it is sigma finite measure space. Now let's look at the second application. Second application, let me just check whether it's recording. Yeah, good. Second application, you notice that here in some sense, okay, my space may be going like this. I truncated it. Okay, Do you remember I drew earlier some picture? Okay, these are my E1, this is my E2, and this is my En, etc. Right. So essentially, I'm trying to truncate the measure space, the x. Okay. Now I'd like to truncate the function. So let L be x, be mu. Okay. No mu arbitrary. Mu arbitrary in the sense that no sigma finite as assumption. Okay. Right. Now I want to define the truncated n. Okay. This is a function. This is equal to f of x if mod f x is less than or equal to n. I equal to 0 otherwise. Right? Again, the picture is very clear. We have drawn such pictures. So this may be, if this is my n, this is my thing. Okay. So my graph is going to be, fn will be this one. It may be negative also. I'm just drawing picture. This is the graph of fn. Yeah. So what we want to do is, again, we want to show f of n. Of course, converges to fx pointwise. Is that clear? Yeah. But again, by Archimedean property. Okay. Fx, choose n such that mod fx is less than n, then for all n greater than or equal to n, fn of x will be fx itself. Yeah. Therefore, this is clear. And we assume, and also notice that less than or equal to mod fx. So it may be real valued, complex valued, extended real valued, I don't care. But if it's extended real valued, we as usual assume it's finite after modifying the function. Okay, for all. Okay. Therefore, I can apply dzt. What does dzt say? Dzt says integral of f and d mu converges to integral of f d mu. That is, look at this. It says this area, okay, converges to the original area as you keep on lifting. Yeah. Okay. So P R. The third application is popularly known as absolute continuity of the Lebesgue integral. Okay. What does it say is, let f belong to L1 of x be mu. It is related to absolute continuous function, but if you don't know what is it, don't worry. In fact, I get the definition of absolutely continuous function by using absolute continuity of the integral. Okay. Anyway, let's not worry about it. Okay. Then what it says is, for any given epsilon, there is a delta positive such that if E is in B and measure of E is less than delta, then integral of, okay, mod f over E is less than epsilon. Okay. Again, you see, don't just understand this just like the theorem. Okay. There is an analogy, right? Suppose I have a sequence an which is absolutely convergent, right? That means given any epsilon positive, there is an n, so that if n is greater than or equal to capital N, then my ak, k from n to infinity, that will be less than epsilon in modulus, right? This is analogous to this. Yeah, right. Again, try to draw picture, you will understand this. Suppose I have something like this. Okay, I have a function. Okay, let's assume it's non-negative. Okay, it's integrable. That means intuitively the area is finite, right? What does it say? It says that, for example, if it is here, I have to choose a delta like this, so that the area will be less than epsilon. Whereas if it is here, I can choose this, right? Okay, just think about in terms of pictures. I don't want to spend time on that. The proof is easy. Since f is in a mod f is in L1, okay, let us look at mod f to the power this n, right? Therefore, given epsilon positive, since I know integral of, so let us assume the loss of generality f is non-negative, therefore I don't have to write ugly notation because I am going to apply only mod f, right? So we know that integral of this one converged integral of f and f, these are all in L1, okay? That means these are all finite, therefore given epsilon positive, there is an n, so that for n greater than or equal to n, okay, this integral of modulus minus f of n, this is less than epsilon. This is what we actually prove, or at least we want this one is, okay, this is less than epsilon, right? Okay, so fix n, said that, okay, and since it's are all non-negative, and you can see this since f of n is less than or equal to f, right? Therefore, this is nothing other than integral of f minus f of n is greater than or equal to 0, right? So that integral of f minus f this n is less than epsilon by 2 over x. So I don't have to worry about modulus now. Is that clear to you? Right? Okay. Right? Okay. Now what do I do? Now let us assume mu of e belong to b, and I do not know what delta I want. Okay, this is what I have to fix. So let us try to do that. So let us try to write down integral of f over f, right? This I can write as integral of f minus f n plus f, right? Over e, right? But this is equal to integral of, again notice that all of them are integrable, therefore this is nothing other than f minus fn over e plus integral of fn over e, right? By monotonicity, this is less than equal to integral of f minus fn over x, and this integral of fn over x. Sorry, fn over e. This I don't want to change. You understand this? Here I don't want to change. Whereas here I am changing. Right? By my choice, I know this is less than epsilon by 2. So, to make sure this fellow is less than epsilon by 2, I want this to be less than epsilon by 2, but this is less than or equal to this epsilon by 2 plus this object. Therefore, what I need is I want integral of f mod n over epsilon is less than epsilon 2. We have to ensure, make sure this happens. But notice that, again, analysis means estimate. Thus, on E, this fellow is less than or equal to n. Therefore, this is less than or equal to integral n over E. Therefore, this is equal to n times measure of E. I want this to be less than epsilon by 2. That means I want mu of E to be less than epsilon by 2n. That means delta E should be 0 less than delta less than s squared by 2n. Yeah? So, what is that? So, let us go through the proof. The first thing is, with our loss of generality, assume f is non-negative. Second, by application to fix an n so that this, the integral f minus the truncated, this is called truncated f at n. or F truncated at n. Okay, that is, we chop it off. Okay, this is truncated. That's less than epsilon by 2. Then what we do is you choose a delta, that n is now fixed, therefore, and epsilon is given, therefore I can define delta, right? And then we prove that inequality. Okay. So learn these three applications. Well, okay, there are a lot of other interesting applications. Suppose f is a continuous function on a closed and bound rule a b to r, we know it's a Riemann integral. Now I want to show it's also it's measurable also, I know. I want to say it's a Lebesgue integral exists. It's Lebesgue integral exists because f is continuous, therefore it's bounded. Let us say mod f is bounded by m. And m is integrable, constant function is integrable on any finite measure space. Yeah. Therefore, yeah, f is integrable. Is that clear? Now, by using f is uniformly continuous on the closed and bounded interval, therefore I can approximate it uniformly by means of step functions. Okay. Therefore, I can apply dominated convergence theorem again. Okay. But I forgot to say, usually they also say as corollary bounded. Suppose my measure space mu of x is finite, let m be any constant, then m is in L1, right? Integral of mod m will be m times mu of x, which is finite, right? Therefore, all constants will be integrable. Therefore, if I have a sequence of measurable integral functions f, I have a sequence of measurable functions fn such that mod fn is less than or equal to m, and if fn converges to f, then integral fn converges to integral f. It is called bounded convergence theorem. Okay. Can you write it on your own? Do I have to? I'll just do it and stop. Assume mu of x is finite and fn's are less than or equal to m. Notice that m is in L1 of x. This m simply means constant function, not constant function belong to L1. And assume that fn converges to f, right? Now they are dominated by an integral function, and notice that the fn's are measurable is enough. Because of this condition, m is integrable, fn's will be integrable automatic. This follows automatically. As a byproduct. And integral fn converges to integral f, or integral mod fn minus f goes to 0. Okay, by dct. Okay, this is called bounded convergence theorem. So I hope you enjoyed these lectures. So in some sense, all the most important results of the Lebesgue integral are proved now. We just have to look at some non-trivial applications so that you become comfortable with that. Okay, that will be my mission for the next few sessions. Okay, please review. We will meet again. Take care. Stay safe.